Presentation on risk assessment, in which I present some basic concepts, tools and approaches. My name is Pieter van Gelder, Professor of Safety Science. Let me start by reminding the words of Jeroen van den Hover earlier in this MOOC. New technologies which we are developing should respect the values which we hold dear. One of these values is safety. Research on responsible innovation therefore includes a proper risk assessment of the new technologies that we develop. With a risk assessment of a technical innovation, we aim to estimate and judge the risk or risks which this new technology could entail. For this, we need to know the following important concepts first: failure, consequences of failure, probability of failure, and finally, risk. Failure is the state or condition of not meeting a desirable or intended objective. For instance, failure of a dike, which function is to protect a low-lying area against flooding from sea, river or a lake, would mean that the hinterland will be flooded. The consequences of failure are usually very diverse. There can be economic consequences, direct and indirect, expressed in monetary terms. There can also be a loss of life, people wounded, damage to nature, historical values and other intangible damage. The probability of failure is a measure of the likelihood that a failure event can occur, expressed on a scale between 0 and 1. The probability of a dike failure should be conditioned per time unit. The probability of a sea dike failure in the Netherlands, for instance, is in the order of 10 to the power minus 4 per year. The consequences of such a failure would be enormous, typically in the order of 100 billion euro if we take only economic consequences into account. This is what we call a low probability high consequence event. Finally, the risk is given by the product of the failure probability multiplied by the consequences of failure. For the dike failure example, the risk of a sea dike failure is given by 10 to the power minus 4 multiplied by 10 to the power 11 is 10 million euro per year. Notice that this is a returning risk over an infinite time horizon. The question whether this risk is acceptable depends very much on what we can do about it. Can we reduce the risk by engineering solutions, preventive measures such as building a stronger and higher dike, or by repression measures, the use of emergency services during the flood? Now, for a proper risk assessment, good models for the probability of failure are needed. This means that we have to look for the causes leading to failure. Such causal analysis can be done on different levels. An example illustrates this best. This is a top view of a low-lying area threatened against possible flooding from different directions. We can have a flood from the sea if dike 1 or the dunes would fail. We can have a flood from the river if dike 2, the sluice or the levee would fail. If one of these failure events occur, the undesired top event, flooding, also occurs. Notice that we use an OR gate in this case. Only one event has to occur in order to realize the top event. We can go one level more detailed and investigate the causes leading to the failure of dike 1. Many cross-sections can be drawn in dike 1. If one of these sections fails, inundation starts to occur and the low-lying areas will be flooded. Again, an OR gate is necessary at this place in the fault tree. The weakest component in the system determines the safety of the low-lying area. In this sense, the area is quite vulnerable. One step deeper in our causal analysis of failure, we can identify are the physical failure mechanisms leading to failure of a cross-section. For instance, overtopping may occur if the water levels and wave heights, indicated by the symbols H and HS, exceed the crest level of the dike, indicated by X. The first two variables are known as stress or loading variables, indicated by S. And the last variable is known as a resistance variable, indicated by R subscript I, to show that it is also space dependent. For the quantification of this failure probability, we need a detailed analysis of the fluctuation over time of the stress variables as well as a detailed analysis of the spatial fluctuation of the resistance variables. Both stress and resistance variables are stochastic variables, which need to be described by probability density functions, with certain mean values, standard deviations and other characteristic parameters. Failure probability increases if the left tail of the resistance distribution further overlaps the right tail of the stress distribution. The causal analysis of failure, which we have conducted on different levels of detail, has been visualized in what we call a fault tree. We can also perform a consequence analysis of failure, in which we visualize the paths of the consequences as a function of different scenarios. Also here an illustration explains best. A low-lying area is protected by 3 dikes, a guard, a sleeper and a dreamer, as shown in the following top view and cross-section. The event tree starts with an undesired initiating event, high water at sea. If the guard is successful, there are no consequences. If the guard fails and the sleeper functions, only polder 1 will be flooded, and so on. All possible scenarios are embedded in this tree, which we refer to as an event tree. In this lecture, we have seen some important approaches in the risk assessment of engineering systems, the fault tree and the event tree approach. A fault tree with only OR gates is called a series system, and we have seen that this is a vulnerable system. A fault tree with only AND gates is called a parallel system, which is a very robust system, since failure of the system only occurs in case all components would fail. In responsible innovation, our preference tends to the parallel systems, where redundancy is present to take over if certain critical components would fail. If we combine the fault tree and the event tree approaches, we create a bow tie, where the left side is a rotated fault tree and the right side an event tree. The center describes the undesired event, failure of the system. Prevention or reducing the probability of accidents can be achieved by eliminating the causes in the fault tree or by adding barriers in the event tree. Thank you for your attention.